Okay, so this is the second half of a problem we started last class period, or a set of problems. And again, it's just drawing the shear force and bending moment diagram. I'm going to kind of shortcut the process a little bit and go ahead and tell you that the reaction on the left side should be W naught L over 2, and the reaction on the right-hand side is also W naught L over 2. Basically half the total load to one side, half to the other. They're both pins, so we know there's no moment. So starting with the shear diagram, do we know the shear at the left side? Yeah, we go up here. What kind of shear force is this for this kind of reaction? That's positive, right? So I'm going to start at a positive value of W naught L over 2. Now on the right-hand side, what kind of shear is this? Negative. So W naught L over 2 negative. So I know where I'm starting, I know where I'm ending. Let's hopefully we can match those points up. So remember, our basic relationship was that the change in shear between any 2 points is the area under the load diagram. So the change in shear between the left side and the right side should be the area under the load diagram. And what is that? Yeah, it's a rectangle, so it would be base times height, so W naught times L. And remember, this load is what? Positive or negative? It's negative. So if I start at WL over 2 and subtract WL, I get minus WL over 2. So that seems to match really well. The next associated relationship is that the slope of the shear diagram is equal to the load. So I look at the load, and the load is a constant value. So that means I'll have a constant slope, and it'll have a value of W naught, and it'll be negative. So when I connect those two, you can see I get a negative constant slope. In fact, if I were to measure that slope, you would see it would be 1 over negative W naught to 1. So there's my shear diagram. Any questions about that? So it looks like the shear starts off at positive, and it linearly decreases to 0, and then continues on to be negative. So let's see how that affects our moment diagram. So looking at the moment diagram, starting at the left side, do we know the moment at the left side? Sure. It's a pin, external pin, so I know it's 0. What about the right-hand side? Same argument can be made, so I know it's 0 there too. So I'm going to start with no moment, have some kind of change, and hit 0 again. Now, according to my relationships between moment and shear, the change in the moment between any 2 points is the area under the shear diagram. So here's an area in the shear diagram. It looks like it's a positive area, and it's a triangle. What's the area of a triangle? 1/2 base times height. So that means if I start at 0, I should add this amount to 0. So that would be W naught L squared over 8. So that means I would have a positive value of W naught L squared over 8. Now what's the shape of the curve between these 2 points? Well, according to our relationship, it should be the value of the shear. And what does the shear start off at? What value is the shear at the far left edge? Well, you go up and it's a positive slope, right? And it decreases to 0. So here's 0 slope. So I know that my curve, so I have a constant, integrate it once, you get linear, integrate that, you should get a parabola or a quadratic curve.
So how did we say WL squared over 8? Is that just like we just...
That's just the area under the shear diagram.
Okay, yeah, you're right.
And it's a triangle. Now, as I go from the midpoint to L, the change in moment between these 2 points should be the area under the shear diagram, which you can see is symmetric here. So again, the area of a triangle, 1/2 base, L over 2, times height, minus W naught L over 2. That gives us negative W naught L squared over 8. So I go subtract it, I get back to 0. The slope of my diagram is given by the shear. At this point, the shear is 0, so that's 0 slope. And then it decreases to a negative value. There's a negative slope. And if I were to pencil that in, it would look something like that. My curve may not look like it, but it should be a symmetric curve.
Yeah, so how are you getting the slopes at the beginning and the end? Like, so just so your parabola looks...
Well, remember our relationship tells us that the slope of the moment diagram is equal to the shear.
Okay,
so the shear starts off positive, so I have a positive slope.
Right.
And it decreases to a 0, which means I have a 0 slope.
Okay.
And then it goes from 0 to negative max.
Yeah, I think I understand that part. I'm just wondering, like, how specifically, like at the beginning, how you know whether to start, like really steep or...
Oh, that's just arbitrary. I mean, if I actually want to do this to scale, right?
Right.
Then I know that the slope of this diagram would actually be here as W naught L over 2. It would have a value, right? But it would immediately decrease to some smaller number. And over on this side, a little harder to see, but my slope here would be minus W naught L over 2, given by the shear there. But we know it's a parabola, so if I know kind of a rough idea of the slope at the beginning of the segment and the end of the segment, that would be good enough. That brings us to another interesting point. Where's the maximum moment occur? Right in the middle, and we know the value. You'll notice that the maximum moment is occurring where the shear is 0. Well, that kind of makes sense, right? If you want to find the maximum value of the moment, if you want to find the maximum of any function, you take the derivative. And what's the derivative of our moment? The shear. So anytime you see the shear go to 0, you're going to probably have a local maximum or minimum in your moment diagram. And we took advantage of that right there. Any other questions about this one? We'll work some more here in a second. Okay.